Hi, I'm Mario Vano. I operate amateur radio station AE0GL near Minneapolis and like to experiment with QRP hardware. So I need a way to measure the spurious outputs of my radio transmitters. I've been doing a series of videos showing my use of the Siglent 1204XE oscilloscope for this purpose. This short video will show how I measure the spurious harmonic output of QRP transmitters with it. It's true that many scopes have FFT tools that are limited, but the Siglent 1204XE seems to work well for the purpose if it's set up properly and its limitations are understood. Mine gives useful results for harmonics below 200 megahertz. Above that frequency, the bandwidth of the analog circuitry will cause incorrect readings. It also makes no attempt to hide any internally generated low-level spurious signals, and one must be aware of any that might be mistaken for signals from your device under test. The transmitter signal must be properly sampled, attenuated, and protected from interference, and the parameters of the analysis must be carefully chosen or the results will be misleading. Internal artifacts generated within the scope need to be identified and accounted for. All devices have some such spurious signals. RF spectrum analysis requires attention to detail. The dynamic range of the analog path can limit the ratio of fundamental to harmonics we can display. With care, we can achieve a 60 to 70 dB dynamic range on this model. I'm going to use the FFT function to display harmonics of the signal transmitted by the radio while it generates a continuous carrier. I'm going to move into the oscilloscope display a little closer so that you can see the settings I'm making and the display a little bit better. Pardon my fingers for being all over the place, but there's no other way to do this. First, we're going to reset the scope setting by pressing the default button. Make sure that only channel 1 is enabled so that you get the highest sampling rate possible. Set the input channel to match the connection method that we're using. In this case, it's by means of a 10 times probe plugged into a T connector at the dummy load that was visible before we zoomed in. So we need to set the channel 1 settings to show that we're using a 10x probe. No. So that everything will scale properly. Make sure you understand the safe input voltage limitations of your own scope and probe to confirm that you are not risking damaging either of them at the RF voltages involved. At power levels higher than about 10 watts, you may need to use a more elaborate sampling method to prevent expensive damage. Now we're going to turn on the transmitter at the desired frequency and power level. I'm using a 5-watt QRP Labs QCX Mini transceiver with the transmitter set to 14.1 megahertz to generate a steady CW signal. Press the Auto Setup button on the scope to get rough level, trigger, and sweep settings. They'll definitely need trimming later, however. Press the Math button and select the FFT operator. In the FFT menus, set the vertical parameters as follows. Units to dBm. It's very important to do this first, or you'll have to redo all of the other settings. We're going to set the reference level to 40 dBm. The reference level is the top of the display, and 40 dBm is approximately 10 watts. And we're going to set the scale to 10 decibels per division, which will give us a range on the screen of almost 80 decibels. We're going to go back to the FFT menu, select horizontal, and set the center frequency to 50 megahertz. And the hertz per division to 10 megahertz. This will show us harmonics up to about 100 megahertz. Going back to the FFT menu, we're going to alter the configuration to set the mode to average 4 sweeps per display. This will make for a somewhat calmer display. Now we need to refine the scope's vertical amplifier and horizontal sweep settings. First, let's check the sweep frequency. If it's too high, there won't be enough samples to resolve the signal accurately, as is the case right now. If it's too low, the display update will be slow or will run out of FFT memory. I'm ending up with a setting of about 10 microseconds per division, which seems to be working well for what we're trying to do. It's very important to then set the input channel's analog gain to avoid clipping or other forms of distortion or loss of dynamic range. I usually get maximum linearity when the display is occupying about 1/3 of the display area. So it's now occupying 1/3 of the analog split on the display. Now we can measure harmonics using the Tools menu in the FFT functions. We need to turn the markers on and then press the Markers on Harmonics button, and it will automatically set markers to all of the harmonics it can find. And it will base this decision on which is the strongest signal that it sees to use as a fundamental. After everything is set up, you can switch to an exclusive display in the config menu, which will make things a lot less cluttered. At any time, you can press the scope's stop button to freeze the image and use the measurement cursors without needing to keep the transmitter keyed. Use the cursors button and we can select the Y cursor type and the source of the cursor measurements to be the math functions. Now we can place the Y1 and Y2 markers to make measurements. I'm placing Y1 on the fundamental, and then we can move Y2 around to measure the level and have it displayed of anything we see on the screen, including the other markers. I'm moving it to marker 2, and the pop-up is showing us that the transmitted signal is 37.6 dBm at the time that the display was frozen, and that Y2, the second harmonic, is minus 23.4 dBm. It also shows us automatically that the difference between the two is minus 61 dB, which is very good. The other harmonics up to the 5th are very, very low and buried in the noise. But if we want to look at the 5th, we can see that it's 70.6 dB down. In this way, we can do all the measuring that we'd like. Now, if I run back on with the transmitter off, as it is, we have one problem we have to account for, and that's that we still see some signals. The first one is that at the fundamental frequency, occasionally we'll see a signal popping up down in the noise, this is around 80 decibels below our reference level, or minus 40 dBm. This is caused by the local oscillator leakage coming from the transmitter. This is an actual measurement that is correct, although it is very, very faint. This is a problem that is common to all direct conversion receivers, and it is not an issue, and it's perfectly legal. But you may have also noticed that you hear that in a receiver tuned to the same frequency. However, we have two other signals that are probably not coming from the transmitter. One is at 62 megahertz, roughly, and is 38 dB, is minus 20.2 dBm, or less. This appears to be a spurious signal that is generated within the oscilloscope, probably by leakage from a clock oscillator. And there's another one at about 75 megahertz, about 32 decibels down. These need to be basically ignored because we know they're not coming from our transmitter, and we could confirm that by disconnecting it, but I'm not going to bother because I'm already aware of this problem. All measuring devices for spectrum have some kind of internal problems like this, and many of them will automatically hide them from you so that you don't see them. Either way, you have to account for them, because if they're hidden, then spurious signals that you generate at those frequencies will be hidden from you as well. In the case of the oscilloscope that I'm using, we need to ignore them ourselves. These spurious signals generated in the measuring equipment and the noise level that you can see down at the bottom of the screen ultimately will determine the range of our measurement accuracy. We're getting approximately a 60 to 70 dB range that we can rely on here. The noise level is about 80 dB below the carrier, and you can see it moving around a bit. If we average longer, we could get a slightly more accurate indication from it. But basically, it's what's going to set the dynamic range of our measurement. I usually save some screen images and keep this set up for future use. It's very useful for many measurements of this type. For part 2 of this video, I'm going to make a similar measurement using the popular TinySA Spectrum analyzer to show you how you would do it with it. It's a very popular tool, and it also provides very good results for this kind of use. First, I'm showing you the setup that we need to drive it. We have to protect its input because it can't withstand very strong signals. So I'm using two 20 decibel 10 watt attenuators in line between the transmitter and it. They're also functioning as dummy loads. I'm now going to switch over to a closer display of the TinySA, and to do that I'll have to stop the video for a moment. Okay, I'm back, and we're now looking at the display of the TinySA. To start, I'm going to reset the device to the default startup settings. And when I do that, you can see that, interestingly enough, we are seeing that local oscillator leakage from the receiver of the transceiver. It has automatically placed a marker on it and is showing us that it is 40 decibels down. I have a preset in this TinySA to add an additional 40 decibels of attenuation. So we're going to use the built-in measurement function, which is capable of measuring harmonics automatically if you give it the fundamental frequency. And when I key down, you can see that we have the fundamental visible now, and it's showing frequencies from 0 to 70 megahertz. However, we're not seeing any harmonics, and that's because the automatic attenuator has set a range that is too narrow to see them. The attenuator has put in 30 decibels of additional attenuation, and this is normally necessary to get accurate readings with this device. In our case, we're going to override that and set a manual attenuation level of 20 instead, minus 20. When we do that, the second harmonic becomes visible. The device is automatically displaying at the top the levels of these harmonics. The first, being the fundamental, is showing up at 39.4 dBm. The second one is showing up at minus 61.7 dBm, give or take. So this is basically the setup you would use for this type of measurements. The results are very comparable to the ones from the oscilloscope, although the oscilloscope has a somewhat wider dynamic range. And as a result, it shows some other spurious signals that we may or may not care to know are there. However, both devices have more than adequate range to ensure legal compliance with the amateur radio laws in most countries at these frequencies. At other frequencies, different harmonic regulations apply. Thank you for watching this video, and I hope it shed a little light on a very confusing subject.